So this is A2U5L3A. There's actually 3 sections, an A, a B, and a C. We're going to start with this first section. And what we're going to do in this section is we're going to analyze polynomial graph behavior. And our goal is to get to the point where we don't have to graph polynomials anymore because we can just look at them and tell what they're going to do. And we do that by graphing a bunch of them and looking at some commonalities. So first of all, we see here the representation of a polynomial function, and I know this may look weird, but if you take it apart, it's really not so hard to understand. Your first number, the a here, that's a constant, so that would be like 3. Then you may or may not have a subscript. X is going to be a variable, and n is an exponent. So this is what this first term might look like. Then when you go to this next term, you look at its relationship. A to the n minus 1 just means if this is the fifth term, if there's 5 terms, this one's going to be 5. Well, this is going to be 4. This would be 3. So your terms go down in their position. It's kind of their position number. All right, you have your variable, whether it's one variable or a bunch of them. And then your exponent is going to decrease by 1. Remember, that's standard form. So what this is actually showing you is a polynomial in standard form, and it ends with your linear term and your a term, just a constant. All right, all coefficients are real numbers, so we're not going to deal with any imaginary numbers. All exponents are whole numbers, so we're not going to deal with any fractional exponents. A to the n is not equal to 0, so that means your first term can't be the 0 term, or there won't be any, and n is a positive integer. So this is setting us up for all nice things. All right, the degree of a polynomial function is the value of its greatest exponent. We've already talked about that, so let's keep that in mind. Now, there is something called parent functions, and that's like the starter for all these graphs. There's a base graph of everything, and any other graph is just a manipulation of it. We've looked at some transformations, so this is just going to point out 6 different parent functions. Now, there are others, but these are the 6 we're going to look at. So first, let's look at the constant. Now, you know a constant is just a number. What that looks like in function form is f of x is equal to c, where c is a number. What that looks like in real life or in a real problem, you would see y equals to a number. All right, that's an example of one. So what would that look like graphed? Well, it's just going to be your horizontal line going straight across. So this is the parent function of a constant polynomial. All right, now for a linear, what's that going to look like in function form? F of x is equal to x. In equation form, that's going to be like y is equal to x. And that would be your example. So what does that look like graphed? Well, that's going to be your straight line, just like that. Next, we have a quadratic. So what does a quadratic look like in function form? Well, that's f of x is equal to x squared. Now remember, these are our parent graphs. So you're not, most of yours are not going to be just x squared. There's going to be other numbers. We are just looking at the parent, at where it all starts. And what that would look like in equation format is y equals x squared. And what that looks like graphed is, yes, your parabola. Now let's move on to cubics. Your cubic in function form would be f of x is equal to x cubed. And your example would be y equals x to the third. And your graph is going to do something really funny. It's kind of going to go up like this way, and down like that way. All right, now for our quartic. In function form, this would be an x to the fourth. In equation form, that would be y equals x to the fourth. And graphed, you're going to get a parabola, but it's going to be a lot narrower, okay? See, compare that to the x squared one. All right, now for quintic, for a 5, Yes, you're going to start with f of x is equal to x to the fifth. An example of that in equation form would be y equals x to the fifth. And graphing that, it's going to look very much like your cubic, only it's just going to be narrower. So it's going to go up like this, down like that, closer to your y-axis. Okay, so let's learn some new vocabulary. Turning points. All of these things changed, well, except for the linear ones. But polynomials, they switch direction. They might turn around and go back on themselves. They go up, they down. But there's points where they change. And the turning point, if a turning point is higher than any nearby point, it is called a relative maximum. And sometimes this is called a local maximum. It's usually referred to as a max. All right, if the turning point is lower than any nearby point, that is called a relative minimum. Also can be referred to as a local and a min. All right, so looking at your graph over here where it says turning points, your relative maximum would be this point up here. See, it's higher than any points around it. So this would be your max, and this is your min. That's the lowest point, and it is also, both of these are the points where those graphs change places. Now the minimum and maximum values both are referred to as extrema. Turning points define where a function is increasing or decreasing. So if I look at this graph over here and I want to tell where does it increase, where does it decrease. All right, starting at the left, which is infinity, as it goes up, that's an increase. So from here to here, that would be an increase. Then from here to here, this next block, that's a decrease. And it stops at your point here. Now what happens from here to here? It's an increase again. So these turning points are the places where decreases and increases start and stop. Okay, now we're just going to look at a graph and we're going to enter it in, we're going to put it in Desmos, and we're going to try to find the relative max and min and the intervals of decrease and increase. And I have already got it graphed here. So what we're looking for is we want this point, we want to find that point and that point. And see, when you put it in Desmos or on a graphing calculator, it's going to give you the points for this. So I just don't want you to think I'm just guessing at these points. When you put this in Desmos and you graph it, you can tap these 2 points. Now look at them. Your high point is at 0.70901 and 4.3. Your low point is at 3.29 and -4. Okay, so let's come back over here, and our relative maximum was at 0.7 and 4.3. If you go back to the graph, that's this point right there. All right, our relative minimum was at 3.29 and -4.30. Once again, if you look back on your graph, see the name of that point is 3.29 and -4.3. Okay. Now your increasing intervals are going to go from, where does it increase? Well, it increases from over here at -infinity all the way to this relative maximum. And then it also increases from this point on up. So we've got 2 intervals of increase, and those would be stated as -infinity to 0.71 and 3.29 on to positive infinity. Now that spot in the middle where it was decreasing, that interval is 0.71 and 3.29. So let's look at number 1. We have this polynomial, and it tells us to graph it using a table. Now I'm going to show you how to use a table, but we're going to use Desmos for the others to graph it. So what you do to use a table, you just pick some numbers for x. And I usually pick 0 and -1, +1, and then we'll go with 1, 2, and 3. You're going to plug each one of these numbers in for x, and then you simplify that side of the equation. It's going to give you a number. That's going to give you your y value. I know y'all have done this a million times. So when you put 0 in, that's going to simplify to -3. When you plug -1 in over here, that's going to simplify to -7. When you plug +1, that's going to simplify to -5. 2 will be -7, and 3 will be -3. Okay, so coming over here to describe all of our behavior, what is the domain? Well, that's going to be your set of real numbers. Overall, this graph is covering everything from x to y because it's going this way and it's going that way. All right, your range is the same way. Set of real numbers, because overall it's going to go all the way up and all the way down. So now our relative max is going to be the one point that is higher than all of the things around it. Now this right here is not a max, and this right here is not going to be a min because it keeps on going. We're looking at the places where it changes direction. It's not changing direction after this, and it's not changing direction over here. So our maximum point is right here, and that is at the point 0 and -3. All right, your minimum is going to be right here. There's one relative minimum, and that's at the point 2, -7. Okay, now we have 3 intervals on this graph because it changes places 2 times, here and here. So our first graph, or our first interval, is from here to here, and that's increasing. And where is that interval? Well, it's from -infinity all the way to 0. That's where it changes. All right, what's our next positive, our next increase from here to here? See, it starts increasing here. So our next increasing interval is going to be from 2 to +infinity. Now that interval in the middle where it is decreasing, right here, we're going to put that down here where it decreases, and that's from 0 to 2. All right, as far as our end behavior, as x goes to the right, or rather, let's do the -infinity first. As x goes to your left, so as x goes this way, what's the end of your graph doing? It's going down, so that's a -infinity. And as x goes towards +infinity, the end of your graph is going up, so that's +infinity, okay? So that's what we're going to do here. And like I said, we are going to cheat a little bit and use Desmos to graph these because that's going to be quicker. So let's look at our next one. And x to the 4th plus x to the 3rd minus 4x squared plus 5. So let's just look at the graph. What's going to be our domain on this graph? Well, as far as x's go, we're going to have the set of real numbers because it's covering them all. Now, the range. When we look at this, now the range is concerned with the up-down. So you see that right here, nothing goes past that. So that's going to be our y is greater than or equal to, and I put too many things here. Hold on. Nope. Okay, y is greater than or equal to -3.31, and let's put it in proper format. Y such that y is greater than or equal to -3.31. Where did I get that number? Well, I tapped right here, and then I rounded off that 3.309 to 3.31. So there's no magic. I'm just using Desmos. Okay, so when we look at our graph, how many maxes and mins are we going to have? How many points do we have? Well, we have two relative minimums, one here and one here. And then we have one relative max right there at 0.05. So let's go ahead and put the relative max is at 0 and 5. And then our relative minimums were at negative 1.84 and negative 3.31. That's why we're using Desmos to graph these, because there's no way we would find those exact points doing it by hand. Okay, and the other relative minimum was 1.09 and 2.95. Okay, so our intervals of increase were from this negative 1.84 and 0 to 1.09 infinity. Those were the intervals where this graph was increasing. And I mean, I'm not going to draw the exact thing, but just so we can recall what it looked like. That was kind of what it looked like. So our decreasing intervals are the intervals from here to here, and from negative infinity down to that point. Both of those are decreasing. So we're going to have from negative infinity to negative 1.84 and 0 to 1.09. Okay, now what about this end behavior? As x goes to the right, our end goes up, so that's positive infinity. And as x goes to the left, our end goes up, so that's also positive infinity. Now, so let's look at another one. Now remember, we are just looking at graphs. We're not really worried about specifics. So if you graph it on Desmos, this is what it's going to look like. And I would sketch it over here just so we can kind of have something to eyeball, but it did this and then it went like that kind of. That's a rough idea. Here's the exact one so we can get the points from it. All right, when we look at this, our domain is going to be the set of real numbers, and our range is also going to be the set of real numbers. All right, our relative maximum. So we look over here, we have one max, and it's at this point right there, 2, 4. So that was an easy one. And our relative minimum, let's look back at the graph, there was one of those, and it's at the point 0, 0. Okay, so where does it increase? Our increasing intervals are going to be from this point to this point. Okay, everything else is going to be a decrease. So from here to here is our increase interval, and that was only from 0 to 2. All right, now your interval of decrease was from negative infinity to 0, and it stopped. It was decreasing from here to here, and then it stopped and went into the increase, and then it started another decrease interval from here to here. So the other decrease interval is going to be from 2 to infinity. But you see, if you put all of them together, you know, if you took your decrease intervals here, and then you did one for your increase, the whole line is covered at some point or another. Okay, our end behavior, well, as x goes to the left, the end goes up, so that's positive infinity. And as x goes to the right towards infinity, it goes down, so that's negative infinity. Okay, let's look at number 4. And on Desmos, this is what our graph is going to look like. Okay, if you kind of want to sketch it, it's going to go, let's see, kind of up to here and back down here, and it makes a little like this. So that's technically what we're looking at, but we're going to use Desmos to get the points. All right, looking at the graph, the domain is the set of real numbers. It's going to use all of the x's, but your range, now you got to be careful because the range is your up-down values. That's what you've got on your y-axis here. Well, you see right here, it never goes above that. So our range is going to involve this point. Let's go back over here to Desmos, and that point is 6.49. So we'll just round that to 6.5, and we're going to say that our range is y such that y is less than or equal to 6.5. Okay, all of your y's are going to be less than that 6.5. All right, maximums and minimums. When I look at my graph over here, I've got 2 maximums and 1 minimum. So let me keep that in mind. And my first maximum is point negative 1.6 and 6.5. That will be close enough. So I'm going to put a negative 1.6 and positive 6.5. And then that other maximum, if you go back and tap those points, that's going to be at 1.16 and negative 1.91. Okay. So there was one point that was a relative minimum, and that point was at point 41 and negative 2.59, just straight off of Desmos. Okay, when we look at our graph, our increasing and decreasing, so let's see what we've got. Where is it increasing? Well, it increases from here to here, and then it increases from here to here. And where does it decrease? Well, it decreases from here to here and here to here. So we're going to have 2 intervals for each thing. Okay, let's look at our increase intervals now. So we go from negative infinity all the way up here, and the coordinate for that is negative 1.57. Then the other increase interval started at about the point 41, and it went over to the point 1.16. Okay, so now we need our decreasing intervals. Well, it is dropping from this point, which on the x-axis, all these points are on the x-axis. On the x-axis, this is negative 1.57 to 0.41 and 1.16 to infinity. So you see, if you went from here to here to here to here, the numbers match, and they make one straight line going across your x-axis. All right, your end behavior, as x approaches negative infinity, f of x approaches negative infinity. And as you go to the right and approach positive infinity, f of x also approaches negative infinity. Okay, let's look at one more. We're going to graph it on Desmos to get a look at it. And that's what your graph is going to look like. There's one max up there and one min over here. And if we go ahead and look at increasing, decreasing, it is going to increase from negative infinity all the way up to this point, and then it's going to have a decreasing interval and then a third increasing. So our domain, once again, is the set of real numbers. And the range on this one was the set of real numbers, because this one kind of did a like that basically. So now your relative maximum was going to be the coordinates for this right here, and I would go over here to Desmos and get that, and it is rounded off negative 0.12 and 0.06. Negative 0.12 and 0.06. Your minimum, if you look back and tap that point, it's going to be at 1.45 and negative 3.76. And I don't really mind, you know, it's not really so much about how many decimal points you go off here or you go out, because we're not trying to get that specific. We're just trying to look at the behaviors of these graphs. All right, your interval of increase is going to be from here all the way up to here, and then also to here. And remember, we're looking at it going across, so we want the x coordinates. All right, so our increase interval is from negative infinity. Oops, let me get a better color. Negative infinity to negative 0.12, and from 1.45 to positive infinity. Now the interval for decreasing was from negative 0.12 to 1.45. And if you notice, it went like this. You had an increase, and then a decrease, and then another increase. Okay, your end behavior as x goes to the left towards negative infinity, the graph goes down, so that's also negative infinity. And as x goes to the right towards positive infinity, your f of x goes towards positive infinity. Okay, we're going to wrap up lesson 3 now by drawing conclusions about all those graphs that we just analyzed. So when you look here in behavior patterns, you see 6 different polynomials that we're going to graph, and I've already got them keyed up on Desmos. We just want to talk about the end behavior of these. So when you look at the first one, look at the end behaviors. As it goes to negative infinity, what happens there? It's going up. And as it goes to positive infinity, it's also going up. So our end behavior here, both of them go to positive infinity. All right, now let's look at number 2, and we're only looking at end behavior. This one, both ends go down. So both of these are negative infinity. Okay, our next graph over here, number 3. Let's see what happens to these ends. Well, the left end goes down and the right end goes up. So that means as x approaches negative infinity, your graph approaches negative infinity, and as it approaches positive infinity, it went to positive. Okay, number 4, negative x cubed plus 5x plus 1. We see it starts high and makes a little dip, and then a mountain, and then it goes back down. So what's going to be our end behavior here? Well, as it goes towards negative infinity, it was going up, so that's positive. As it was going towards positive infinity, it was going down, so that's negative. All right, now let's look at the next one. Let's pay attention to the end behaviors. Both ends are going up in the positive direction. So as it goes towards negative infinity, that's positive. And as it went towards positive infinity, it was still positive. Okay, now our last graph looks like this. Both ends are going down. So as it went from negative infinity, it went to negative infinity, and as it headed towards positive infinity, the end headed towards negative infinity. Now that we have all that figured out, let's draw some conclusions into this chart down here. There are 2 things that are going to determine your end behavior, and that is the degree of your polynomial, so that's your highest exponent, and whether your leading coefficient is positive or negative. And if you look at this chart, let's look at first all the even degrees. This one is even, this one is even. 3 and 4 are odd, 5 and 6 are even. What do you notice in common about these? They all go the same direction, don't they? It's either both positive or both negative. Whereas, if you look at the ones with the odd, they both went opposite directions. So that's the first conclusion. And what we're going to say is if the degree is even, they're going to go the same direction. If it's positive, both ends go up. If it's negative, both ends go down. Now, if you have an odd degree, like numbers 3 and 4, they went opposite directions. Which direction did they go? Well, if the coefficient was positive, then your first one was negative and your second one was positive. In other words, if it's positive, your end result is going to be positive. If it's negative, it was the opposite way. And I should have drawn arrows for this. This way went down, this way went up. This way went up, this way went down. Okay? So let's put this into practice. We're going to look at some and we're going to see if we can determine end behavior without ever having to graph anything. So let's look at number 7. What is the degree of number 7? So you look at your exponents. What's your highest exponent? Well, it's a 1, which is odd. That number is odd. Now, is your leading coefficient positive or negative? It's negative. So what is the end behavior if it is odd and negative? Well, that's going to be right here. So your end behavior is up and then down. All right, now let's look at number 8. What is your degree? Right there. It's 2, so that's even. So that right there tells you they're both going to go the same direction. Now, leading coefficient is positive. So that means they're going to both go up. Okay? All right, number 9. What is your degree? The degree is 3. So that's an odd number. So that lets you know you're going to have 1 in each direction. So your leading coefficient is negative, and that means it's going to end on the downward slide. So the other one's going to be upward, positive, infinity, negative. Okay? Let's look at a few more. Number 10, first of all, what is your degree? It's 4. That's even. So that means they're going to go the same direction. Your coefficient is negative. So that means they're both going to go down. Both ends go down. All right, on number 11, you've got a 5 for your degree, and that is odd. So you know they're going to go opposite directions. Your leading coefficient is positive. So that means it's going to end on the positive. All right. Number 12, your degree is 4. That's even. So you know it's going both directions. Your leading coefficient is positive. So that means what? You're going to go up and up. All right, for number 13, that degree is 7, which is odd. So that lets you know it's going to go opposite directions. And your leading coefficient is negative. So what does that mean? It's going to end with the negative. So it's going to look like this. The end behavior will look like that. Okay, let's look at number 14 now. Our degree is 2. So that's even. So that tells us our ends are going to go the same direction. Our coefficient is negative. So that means they're going to both go down. Okay? All right, now in this next section, we are going to look at number 15 and 16, and we want to know, determine the sign of the leading coefficient and whether the function has an even or odd degree. Well, that's going to be easy. Number 15, they both go down. So what does that tell you? That the degree was even because they're both going the same direction, and that your coefficient was negative because they're going down. All right, on number 16, you have an odd degree because both ends are going opposite directions, and since the end to the right is going up, that means it's positive. Okay? We're almost done. Okay, for number 17 and 18, they want us to look at the end behaviors, and they want us to check the functions that would be possible for. So for number 17, we look at these two behaviors. They're both the same. So that tells you that you have an even degree. And since they're both negative, that tells you it's going to be a negative coefficient. All right, so what would that be possible for? Well, this one right here has an even degree of 4 and a negative coefficient. And this one here has an even degree and a negative coefficient. So those are going to be the two there. Okay, on number 18, our end behaviors go opposite direction. So that tells you, first of all, you're going to have an odd degree. Now it ends on the positive one. So that tells you that it's going to be a positive coefficient. So let's see which ones have an odd degree and a positive coefficient. Well, this one has odd degree and positive, so it's possible. This has odd degree and possible and positive, so it's possible. The other three are negative, so I don't even have to look to see if they're odd or not. All right. This one, our end behaviors go opposite direction, so that tells you that your degree is odd. And it ends with the negative, so that means your coefficient is going to be negative. So let's go find an odd degree negative coefficient. Well, there's one. And odd degree negative coefficient right there. And odd degree negative coefficient there. Last but not least, both of them go the same direction, so that tells you your degree is even. And your last one is positive, so that tells you that your coefficient is positive. All right, so let's find an even degree and a positive coefficient. Well, here's one. And even, this one's even, but it's got a negative. This one's even and positive, so it's possible. This one's even and positive, so it's possible. And that is all. Okay, now you have a document that you can practice this on. So feel free to use Desmos to graph any of those and then analyze, and let me know if you have any questions.